Math 2414, Calculus 2, Section 9.2, Calculus with Parametric Curves, Video 8 of 9, Example 4. This video has two parts. I haven't written Part B yet because it would spoil the answer to Part A, or at least the setup for Part A. So when we get to Part B, I'll tell you what the what if is. And I also need to do a little bit of damage control from the previous video. In the previous video, we set up the integral to calculate the arc length of a curve to find parametrically, whose x-coordinate was a function of t and whose y-coordinate was a function of t, over an interval of t values. But what I neglected to mention was that the curve can't retrace itself. For example, if we had a curve that did this number, went back to its beginning and retraced itself, we wouldn't want to use the range of parameters that allowed it to retrace itself. Otherwise, we're getting a longer arc length than this curve actually is. So when you're calculating arc length, there is the condition that the curve does not retrace itself over that interval. And in Part B, we'll show you what would happen if you did. All right, the first Part A. Using parametric equations, find the circumference of a circle with radius r. Now, being Calculus 2 students, you should know the circumference of a circle, the formula for the circumference of a circle. But we're about to do the calculus that verifies that it's the correct formula. If we're going to find the circumference of a circle with radius r using parametric equations, the first thing we have to do is define this circle parametrically. And thinking back to what we did in 9.1, I'm not sure if we did. So maybe more important than doing this example is showing you how to parameterize a circle. It's actually pretty easy. If you go all the way back to trigonometry, where you defined an angle theta in radians and you calculated the coordinates on this circle, not necessarily a unit circle, in terms of the angle that you rotated. Well, if we were to drop a triangle here and put x and y to represent the x and the y coordinates, it's not too hard to come up with the equations. The equation connecting x, r, and theta is a cosine equation, since x is adjacent to theta. Cosine of theta is x over r. That means x equals r cosine theta. And similarly for the y-coordinate, since the y is opposite to theta, sine of theta is equal to y over r, which means y is equal to r sine theta. Now, if we treat the r as a constant, so we have a circle with a fixed radius, these are your parametric equations. So if it wasn't said before, I'm about to say it now. The parametric equations, or rather I shouldn't say the, but some parametric equations for a circle. There's an infinite number of ways to parameterize any curve. But the most common parametric equations for a circle are x equals r cosine theta and y equals r sine theta. By the way, these two equations will be critical in section 9.3. All right, so we're going to use those as our parametric equations for a circle. And if we're going to find the arc length, we need to pick values of theta that make one complete revolution around the circle. Well, that's not too hard to think. Theta equals 0 would start me over here on the right side. And since theta is measuring the angle I'm rotating, to get all the way back over here, I would have to make one complete revolution, which would be theta equals 2 pi. So our arc length is going to be the integral from 0 to 2 pi of something. That something is going to be the square root of the sum of the squares of the derivatives with respect to t. So now we just have to take our derivatives of these equations. Well, they're pretty easy. If x is r cosine theta, I'm sorry, I kept writing t's, we're doing thetas. Again, the name of the parameter is irrelevant, but you should at least be consistent within a given problem. If x is r cosine theta, then dx d theta. Remember, we're treating the r as a constant, so it's a constant multiple, so it sits there, and the derivative of cosine is negative sine. That means dx d theta equals negative r sine theta. What is dy d theta? Well, same story. R is a constant multiple, so it sits there while we differentiate the sine theta. The derivative of sine theta is cosine theta. So the derivative of y with respect to theta is r cosine theta. Those get inserted into our arc length integral. I'm erasing it because I don't think I left enough space. The integral of the square root of the sum of the squares of the derivatives. The derivative of the x function is negative r sine theta, so that's going to get squared. The derivative of the y function is r cosine theta, that's going to get squared. We're going to d theta that. Now this looks like a complicated integral, but it's actually pretty simple. You can probably see through it. If we square each half of the addition problems, we get negative squared is positive, so it's gone. R squared is r squared, and sine squared is sine squared. On the other side of the addition, we get r squared cosine squared. D theta. Well, you see it? Under the square root, there's a common factor of r squared. If we factor that out, under the square root, we're left with sine squared plus cosine squared. And as you all should know, that's equal to 1. So let's see if we can multitask here. Sine squared plus cosine squared is 1. Sine squared theta plus cosine squared theta is 1. 1 times r squared is r squared. And the square root of r squared is r, if we can assume that r is greater than or equal to 0, but it's a radius, so yeah, it's greater than or equal to 0. Well, this suddenly becomes easy. What's the integral of r d theta? If you said 1/2 r squared, you didn't hear the d theta part. The r is a constant in relation to theta, so the integral of r is r theta. Now because we have two variables, I'm going to explicitly say theta equals 0 to theta equals pi over 2 to let you know those are going in for theta. When I substitute 2 pi for theta, I get r times 2 pi, or 2 pi r, minus, when I substitute 0, I get r times 0. Well, that's just 0, and we're left with 2 pi r, which is the formula for the circumference of a circle. So yeah, that's the proof that the formula for the circumference of a circle of radius r is circumference is 2 pi r. All right. So what's this part B? What if? Well, what if we were to parameterize the circle this way? X equals r cosine 2 theta. Let me write this a little cleaner. What if we had x equals r cosine 2 theta and y equals r sine 2 theta? Now, why am I putting 2's in there? Well, first off, I can. Because if I were to square both sides of these and add them, and I didn't do that with these, but if you were to square them and add them, well, you already know what happens if you square these and add them. You get r squared, and you get cosine squared plus sine squared. Factor out the r squared, you get sine squared plus cosine squared, which is 1. So if I square these and add them, I get x squared plus y squared. If I square these and add them, I get r squared. X squared plus y squared equals r squared. It's the equation of a circle. Same thing would happen here regardless of the 2. If I square both sides and add the lefts, I get x squared plus y squared. If I squared both sides and add them on the right, I get r squared cosine squared 2 theta plus r squared sine squared 2 theta. I'm basically playing this scheme again. The only difference is the thetas have the 2, but as long as they match, the sum of their squares is 1, and we end up getting x squared plus y squared equals r squared. So that is another parameterization of the circle, but what's the effect of putting the 2 in front of the theta? Essentially, the 2 in front of the theta doubles how fast it takes, it makes the point travel twice as fast around the circle. So for example, if I put theta equals 0, I'm going to be here. Think about it. Cosine of 0 is 1, sine of 0 is 0. So we get r comma 0, which is over here. But what if I put in pi, which normally would put us over here? If I put in pi, it gets doubled, becomes a 2 pi, and we actually wind up over here. So if you were to parameterize this circle by putting a 2 in front of the thetas, you would still get the circle. But if you went from 0 to 2 pi, after half of that interval, you would be back here. Because you would be doubling the pi before you took the trig functions. So halfway across the interval, I'm retracing the circle and I don't mean to do that yet. So after only going to theta equals pi, I've already made a complete revolution. If I keep going to 2 pi, I'm going to trace out the circle twice. Well, if I trace out the circle twice, what do you think its arc length would be? Remember, tracing it out once was 2 pi r. But if I trace it out again, I'll pick up a second 2 pi r. In other words, I'll get 2 of these. I should get 4 pi r. And we would get 4 pi r because when we took the derivatives, if you take the derivatives of the chain rule will throw an extra 2 in front. The 2's would be here. They would get squared and become 4's. There would be a 4 here. It would get square rooted and make a 2 and basically double the answer. So you have to be careful when you're doing parametric equations and arc length, because if you don't check your graph, you might draw it out twice. In general, think of this number in front of the theta as an accelerator on how fast you're going around the unit circle. If the coefficient of the parameter is 1, it takes you 1 trip around the unit circle. But if your coefficient is 2, but your interval doesn't change, it takes you on 2 trips in the same amount of time, meaning that you went around twice as fast. If I put a 10 in front of here and kept the interval the same, I would make 10 revolutions around the circle in the same time span, meaning that I'm going 10 times as fast. So you have to be really careful when you're doing arc length and you don't have the graph, especially if it's something that is periodic, sines and cosines, because at some point, under most circumstances, at some point, the curve's going to start retracing itself. If it's not sines or cosines, you usually don't have to worry. We're going to take a look at one more example. It'll be the last video. And we'll go back to our old friend, the cycloid. And you can probably predict that the question I'm going to ask is, what's the arc length of one arch on a cycloid?